go. Ladies and gentlemen, class recording has started. The next section of Chapter 7 deals with the idea of conservation of momentum. Before your lab last week, we kind of talked about the ideas of conservation, how it applies to momentum. First, when we say that something is conserved, right? What does that mean? It doesn't change, stays the same. And that's what it means here as well. We're just dealing with conservation. Before we can get into conservation of momentum, though, we have to talk about a really important concept that relates to conservation of momentum, and that is Newton's third law. Before we do Newton's third law, let's review quickly. Newton's first law. Newton's first law gets summarized in one word. What is that one word? Inertia. Inertia deals with something that, or when objects do what?
Maintain and rest.
Okay.
They want to do what they were doing.
Right. Inertia in Newton's first law deals with things staying the same, right? Whatever they are currently doing, they are going to continue doing. On the other hand, Newton's second law deals with what? If Newton's first law deals with things staying the same,
It talks about change.
talks about changing, things changing. And the word we use to represent things
Net
changing
force and
is net force and mass both affect what, Grace?
Delta.
Momentum.
They affect the
Force.
acceleration. Right?
Sorry.
Newton's first law deals
So
with
right.
inertia. Newton's second law deals with acceleration. And we did a bunch of problems where we used sigma F equals m times a to summarize the ideas that force and mass both affect the acceleration, but Newton's second law deals with acceleration. Good there. All right. Newton's third law.
Every action has an opposite and equal reaction.
Newton's third law gets summarized with the phrase action-reaction. As it says on the front page of your packet, forces always come in pairs. And, key points, for every action, there is a reaction acting on a different object. The action-reaction forces are equal in magnitude, but opposites in direction. So, let's use an example to illustrate Newton's third law. As many examples will be for the next 2 weeks, maybe less, maybe more, I will use anything Winter Olympics related to explain things to you. So, let's say, no, Bodhi doesn't work good in this example here. We can use Bechtel, if you want names, right? Let's use Charlie Davis and Merrill White. Gold medal winners, baby. Yeah. Right. So, in case you don't know, ice dancing couple, right? Well, you can argue the merits of, what ice dancing is, and whether it's a sport or not. I don't know. You can argue that. I'm not going to get into that right now. But so let's say here's Charlie and Merrill, right? At the beginning of their routine, I don't know if they did this at the beginning of their routine or not, but let's say they're standing still. And there is a force applied. Okay? Now, because of this force, right? Oh, I was going to group these together, right? Because of this force, blue pushes on red, and so red starts moving in that direction.
Which one's the boy?
Okay? Which one do you want to be the boy, Bechtel?
The blue.
Okay, so Charlie pushes on Merrill. Merrill starts moving. Okay? However, as you may have noticed,
Blue should be moving.
okay, blue will also start moving, but blue will start moving in this direction. Okay? Even though technically blue applied the force to red, blue starts moving as well. Because, as we just talked, forces come in pairs. Blue applies what we call an action force to red. Physically, intentionally applying that force. But what we find out is that blue can't apply a force to red without red applying a force back to blue. That force is equal in magnitude, right? Here, let's do this. Let's get rid of this. So that force is equal in magnitude. So I'm going to take this force and I'm going to clone it, right? So it's the same. But it is opposite in direction. So now that force that blue applied to red, red automatically applies that force back to blue. Same amount, different direction. It's not a conscious thing, it just happens. So we have equal forces in the opposite direction, and both of these objects start moving. Now, there is a problem with Newton's third law. If you think about it critically at this point, you might be running into a roadblock. It might be similar to the roadblock that the horse in this comic strip, which is on the back of page 1. So if you want to flip it there. Yeah. All right.
I did do it in physical science. That's where I got it from.
This horse is having a problem, other than the fact he can talk. Okay. So, in the first frame, it says the farmer has got his horse hitched up to, or he's got the wagon hitched up to the horse, and he says, "Giddy up, pull this cart so we can get going." And the horse says, "No can do." So the horse says, "You see, if I pull on the cart will pull back on me. By Newton's third law, forces are equal and opposite, so they will cancel." And then he says, "A net force of 0 won't get us going." So if you've been paying attention up until this point, some of you have, some of you haven't, we talked a lot about that idea of multiple forces acting on an object, adding up all the forces. If you hear equal and opposite, and we add them together, what do we get? 0. And if there's 0 net force, what happens? Nothing, right? Nothing changes. There is no acceleration. That would mean that if what the horse is arguing is if Newton's third law is true, what should we see out there in the real world? Or what shouldn't we see out there in the real world? We shouldn't see anything moving or anything changing what it's doing. Because if each force comes in a pair, and those pairs are equal and opposite, they should cancel each other out and nothing should happen. Is that what happens in the real world?
No.
Obviously not. So let's take a look now at a separate drawing that I'm just going to draw here. Okay. Here's the cart. Okay. And then, please forgive me for my poor art skills. Okay. Alright. We'll give him a big bushy
What
tail.
about a teacher that was actually really good at art?
Alright. And then we'll see here. We'll give him a little mane. Right? So there's his mane. Okay.
I want to see his name.
There we go.
That was really good.
Actually, in the last chapter, or in the last class, it was sitting there, and Rochelle Bish was in that class. And she like had this like art. She had this like perfect drawing of a horse like on her paper, and I was like, mine doesn't look like. was like a perfect. It's like Black Beauty, like John Connor, and I was like, man. So, I have a stick figure horse. So. Anyway, so let's go here. Oh, easy. What do you want to call him?
Woody.
Bechtel? So. All right, Jerry the horse. I mean, I suppose we could call him Mr. Ed, seeing how he talks, but you know, but. All right, so this is what the horse is arguing. The horse is arguing that if he pulls on the cart, right? The cart is going to pull on him with the same force in the opposite direction. And he's arguing that these forces will cancel and it's not going to go anywhere. But we can use modern technology to show the horse that he is wrong. And that modern technology appears in the form of a spotlight. Yeah. All right. So, right now, I'm just showing you the wagon. And if we look at the picture of the wagon as I've drawn it, how many forces is that wagon experiencing in my picture?
One.
One.
Well,
In my picture.
okay.
There are other forces. We'll disregard those forces right now. Okay? It is experiencing one force in this picture. And because of that force, what would it start doing? It would start moving towards the right. There's nothing to balance it out. It would start moving. Now, if we shift our focus to the horse,
Wow.
how many forces is this horse experiencing in the picture?
I'm just focused on his smile.
Yeah, I mean, he's a happy horse. I mean, you know why? Because he thinks he's going to get out of pulling the cart because he thinks he outsmarted the farmer, you know? But we'll see here in a second that really the farmer is going to be the one who's laughing in this case. Okay? So, how's going over there? Is it okay?
That's good.
All right.
Your play seems to be struggling.
Well, he hasn't been here in like a week and a half, so, you know.
Use I'm not allowed to use that word in school. It creates
All right. So, in this picture, as I have it drawn up on the board, this horse is only experiencing one force. And because of that force, it would start moving. But it would start moving which way? Backwards. Do these two forces cancel each other out?
No, the math depends. Right?
No, doesn't depend. They can't cancel each other out. Why?
Because they're not on the same object.
They're not on the same object. Forces that don't act on the same thing can't add up to zero. So the horse thinks he's being tricky, right? But really,
He's just lazy.
yeah, he's just lazy. Yeah. If this was the case, what would happen in our situation here? Sorry, wait, scratch that question.
Yeah, but they're connected.
Sorry, scratch that question. They have to be connected, that's how this happens, right? Horse pulls on cart, cart pulls on horse. So, do they cancel each other out?
No.
No. Why? They're not on the same thing. Action-reaction forces always act on different objects. So this is back to the first page. Okay? As a result, the two forces do not cancel. So action-reaction pairs are equal and they are opposite, but because they act on different objects, they don't cancel each other out. Okay? Going back to this picture, can these be the only forces that are involved in this interaction? No. If these were the only two forces that were involved in this interaction, what would happen?
Nothing.
The horse and the cart would crash into each other. Where?
The Center.
Somewhere in the middle. And that's clearly not what happens, right? There is another factor that we have to consider here, another object. And that object is the Earth, not to scale.
Thank God you do that in.
Yeah, I want you guys to know. So, that's almost so
Huge words.
So, all right. Anytime this horse takes a step, in order for that to happen, he has to do something first. Anytime you take a step, or anytime you jump, or anytime you try to stop yourself, you have to do something first. And that something that you have to do is you have to push on the ground. Whether it's walking forward, or whether it's jumping straight up, or whether it's stopping yourself from going forward, you push on the ground. If you push on the ground, what automatically happens?
Ground pushes back.
The ground pushes back. Paul, how hard?
Just equally.
Equally, but,
In opposite direction.
okay? So, now we got this going on, right? So, in this case, it's not so much the force that the horse is applying to the cart that the farmer is concerned with. The farmer is concerned that the horse pushes on what? The ground. Because if the horse pushes on the ground's going to push back. And now, if we spotlight the horse, expand our spotlight here a little bit. Is this horse going to move?
Yeah.
Yeah. Which way?
Forward.
To the right, because there's a bigger force that way than the other way. So, as you can see from the comic strip, the farmer goes, hey, just push backwards on the ground. By Newton's third law, the ground will push forward on you. Both of these are Newton's third law action-reaction pairs. In this case, right, the horse pushes on the ground pushes back forward. And then the farmer taunts the horse by saying, hey, this ground is doing a great job, right? Because you realize the ground is pushing forward, okay? And then the horse responds with physics, grumble physics, which I'm sure some of you can share that sentiment with the horse. All right, so tomorrow we get into how does this apply to conservation of momentum, and what does that mean for how things move, and why you have to be careful when you're shooting your shotgun, which I'm sure all of you have extensive experience with.
Yes, I did.